right, today, this video, we will be covering phenol. All right, how do we form phenol and what are the reactions of phenol? All right, so we're gonna see a series of reaction, all right, in a step-by-step manner. Now, the first one, I'm gonna start off with how do we form phenol? Okay, in the Cambridge syllabus, there's only one way to form phenol. All right, and the way to form phenol is actually the decomposition of the diazonium ion. So let's start with a phenyl diazonium ion. Okay, so we will start with the phenyl diazonium ion here. So this is the, or benzene diazonium ion. Okay, so this is called as benzene diazonium ion. All right, this one. Now, how was this formed is due to the diazotization process. Okay, so now, if your benzene diazonium ion, okay, add with water, temperature above 10. All right, you can use temperature above 10 or you can use the word boil in water, but you need to use water. Okay, so then it will decompose. So this is a decomposition process. Then it will form phenol and nitrogen gas. Okay, yeah. So this is in general, how do they decompose to form your phenol. Now, in terms of balancing equation, do you think we are able to balance the equation? We just need to put H plus here. Okay, so this would be the balance equation on how to form phenol. It is actually from the decomposition of the benzene diazonium ion above 10, or you can just say boil in water. But in the equation, you need to show H2O. Otherwise, you won't be able to explain how come there's an OH on your ring. Okay, so this is how we form your phenol. Now, subsequently, okay, we will be talking about what are the reactions of phenol. Okay, now, so for phenol, what can they form? So maybe I shall shift, okay, the balance equation. All right, maybe I should put it down here. So let me just put this nitrogen down here, nitrogen gas, and H plus. Okay, they are not our main focus. So let me just erase this. Okay, now for the reactions of phenol, I'm going to split it to two parts. Okay, now the first part on top is to react with the OH group. Okay, so react with the OH on the phenol. So there are three things. Number one, you can react with Na, which is the sodium metal. All right, so here, phenol, react with your sodium metal to form sodium phenoxide, O minus Na plus. All right, and your hydrogen gas. I usually will write O minus Na plus to indicate there's an ionic bonding at a particular corner. So it's not mandatory to put a minus and positive. So we call this sodium phenoxide. So what is the type of reaction here? The type of reaction here is considered as redox. All right, because why? Sodium was oxidized, your hydrogen was reduced. Okay, so I shall not put in the arrow because it will make it more messy. Now, that is to just react on the OH on the phenol, not attacking the ring yet. Okay, now the second, phenol can react with NaOH. Okay, so in fact, phenol is normally dissolved in NaOH. Why? Because phenol is a white crystalline solid. So it is partially soluble in water. Even though it has an OH, I know it can form hydrogen bonding, but because of the big aromatic ring, which is very non-polar, so hence it will make it partially soluble with water, not fully soluble, partially. Okay, so normally we will use sodium hydroxide to help the phenol to dissolve so that your phenol can be in a liquid form. Otherwise, it's going to be a solid. Okay, so phenol and NaOH. Okay, and therefore, same thing, you will form your sodium phenoxide and H2O. So what is the type of reaction here? You can say acid-base. All right, it can be an acid-base because one donated proton, one accepted proton, or it can be neutralization. Okay, now, is there any observation for the first two? Well, for the first one, reacting with sodium, you can see effervescence of phasing of hydrogen gas. For the second one, probably you will just see the solid dissolve. All right, nothing come out. All right, so probably I'll just write solid dissolve, where the solid disappear in terms of observation. Now, the third one, okay, let me just draw a line here. The third one is esterification. Esterification with acyl chloride. All right, now this one, I'll just put a star here. Okay, please make sure you do not make careless mistakes. So phenol can only be esterified with acyl chloride. Okay, so I'll draw a phenol and we draw an acyl chloride. So I'd like to draw it this way. So this compound is called ethanol chloride. Okay, and then we will remove a small molecule. Okay, and therefore you will form an ester bond like this, ester bond. There you go, NHCl. Now, what type of reaction is this? If we're talking about type, all right, then type means condensation. Please don't write esterification as your type of reaction. Please write condensation. How do we name this product, which is your ester? We call this ethyl ethyl benzoate. Benzoate. Oh no, the other way around. Sorry, my bad. It's called phenyl ethanoate. My bad. Okay, right? So phenol can only be esterified with acyl chloride. Okay, now if you think about carboxylic acid like this, okay, now this is no reaction. Phenol and carboxylic acid, and if you try to use concentrated sulfuric acid, heat under reflux, this is a no process. Okay, yeah, please take note on that. So there are three reactions that will react with the OH part on the phenol. Okay, now I want to continue with the second part. Okay, so maybe I'll just zoom a little bit. Okay, so this will give you the whole picture on the three reactions with the OH on the phenol. Now, zoom out. I would like to draw another arrow here. Okay, so now we're going to talk about part two, which is what are the reactions, okay, on the ring, okay? So we want to react with the ring on the phenol. So you cannot touch the OH part. You only can touch the ring. Now, if you want to react with the ring on the phenol, that means it's just like your normal benzene reaction. Okay, so the first one, okay, we learned that there are four reactions of benzene. Now, the first one is halogenation. Halogenation. Okay, like this. Now, halogenation, normally, we will, for phenol, we usually use bromine water, AQs. Okay, AQ. Now, it is a must to write AQ. If not, then you spell out bromine water, like this. The water is mandatory. You cannot just Br2 in your paper. Cannot. Okay. Now, if they want to give you Cl2, then fine. I mean, you just apply accordingly. But usually we will ask bromine because then bromine, you can see the color decolorizes. Okay. So very quickly, this one. Okay. Now, phenol will react with bromine water. Okay. Aqueous here is very important. Now, then it will form tribromo. Okay. Your bromine here at position 2, position 4, and position 6. So we call this 2,4,6. All right, 2,4,6 tribromophenol. Now, this is a white PPT, okay? And your bromine, orange-brown color will decolorizes, okay? So when you see bromine decolorizes, right, normally I think about two things. Number one, CC double bond, which is alkene. Number two, which is phenol. Number three, another one, phenylamine. All right, let's do a side track. If this one was changed to phenylamine, the same thing will occur. You're going to get 2,4,6 tribromophenylamine, also white PPT, also bromine water, the color will decolorizes. So when bromine color decolorizes, I would think about three things, which is a double bond, CC double bond, phenol, or a phenylamine. Okay, very important. Now, common mistake. Yes, many students will know that tribromine will sit on the ring. Okay, so hence the common mistake here student will do is they put 1.5 Br2. Okay, but when you do that, right, then you won't be coming up with the 3 HBr here. Like I can cancel off here. Now, this is incorrect. Okay, incorrect, because the reaction here involves electrophilic substitution. H plus will come out. So that means there is 3 H plus come out because there's 3 bromine that is substituted on the ring. So hence, it's only right that Br2 is used, all right, as in 3 Br2 is being used. Therefore, you will come up with 3 HBr. So the red color pen is a common mistake. Okay, this is called red color pen, common mistake. Don't do that. The blue color pen is the correct version. Okay, you must come up with the 3H plus. So this is an electrophilic substitution. All right. Now, conventionally, when you do a halogenation on the benzene ring, all right, as you can see, we are only touching the ring on the phenol. We did not touch the OH on the phenol. We only touched the ring on the phenol. Okay, so this is actually electrophilic substitution. If traditionally, when we learn about halogenation of the benzene ring, we normally need a catalyst, which is like FeBr3. So a catalyst here is not needed. All right, so I would like to put a note over here. Okay, we will say that FeBr3 catalyst is not needed. Okay, is not needed. Now, therefore, of course, a question will come out over here. Okay, why we do not need a catalyst over here? All right, in other words, why phenol is more reactive compared to benzene? So benzene here requires a catalyst. Benzene, you need the catalyst, FeBr3 catalyst for your halogenation. But when it comes to a phenol, you don't need the FeBr3 catalyst. Okay, now why is that so? All right, why is that so? So 3-pointer in exam. Okay, mark number 1. Okay, mark number 1. Mark number 1. The lone pair electron on oxygen is delocalized into the ring. So when you have a OH on the benzene ring, the lone pair on oxygen will be delocalized into the ring. Mark number 2. You will increase the electron density in the ring. Last mark. So when your electron density in the ring increases, all right, you are able to polarize electrophile easily. Okay, or in other words, they say attract electrophile easily. 3 marks. Okay, so this is also the same reason why phenylamine, okay, and your bromine water do not require catalyst. All right, it's always these 3 bullet points. So maybe they say 3 bullet point, 2 marks, 2 bullet point, 1 mark. Or maybe if they're generous enough, every point here is 1 mark. Okay, so phenol and phenylamine, they are a more reactive version of a benzene ring. Hence, they do not require a catalyst. Okay, so the first reaction on the ring is halogenation. Now, the second reaction on the ring is nitration. Okay, nitration. So for nitration here, we will use dilute nitric acid. Okay, so it's either dilute or you AQ. So then you will form, okay, 2 nitrophenol, or you can form a 4 nitrophenol like this. Both are isomers. They are positional isomers. So I have covered how to know the position where the incoming electrophile will be situated at, and I'll just leave a link somewhere in this video. You can go and click and watch it. Okay, so OH is an activator, so therefore it will direct incoming electrophile, which is your nitronium ion, to the position 2 and the position 4. Now to balance the equation, then you will get H2O over here. Now, conventionally, like I said, normally, if you talk about a benzene ring, a benzene ring alone, all right, what do you need? You need your concentrated H2SO4 catalyst for a benzene ring. But when you play with phenol, okay, you don't need the catalyst. We see similarities again here. Benzene need catalyst. Phenol don't need catalyst. And probably they're going to ask you the same reason as well. Can you please explain why benzene require concentrated sulfuric acid and 55 degrees Celsius? Yes, there's another one, 55 degrees Celsius. All right. Whereas phenol, we just go by room temperature. Why phenol always easier? All right, why benzene is more difficult? That's why we require a lot of catalysts and maybe, temperature to help the reaction to occur. Same reason. You go to the same M1, M2, and M3 discussed. Okay, so you clearly must know the difference between a benzene and a phenol. Okay, so out of the 4 reactions, halogenation, nitration are the main 2 highlight, main 2 focus. Of course, if you want to talk about the third one, which is Friedel-Craft alkylation, okay, Friedel-Craft alkylation, and number 4, Friedel-Craft acylation. This one, the condition will remain status quo like a benzene, all right? They still need the halogen carrier, all right? So to complete the 4 reactions on the benzene ring of a phenol compound. So we're all only attacking the ring, not the OH, okay? So this one, for example, alkylation, let's say you want to put an ethyl group, you need a halogenate alkane, and all Friedel-Craft reaction requires heat. So therefore, you need your catalyst. Let's put AlCl3, okay, as the catalyst. Same thing, you will get your ethyl group here on position 2, or you can come out at position 4, okay, like this. And then come out with HCl. That's the balance equation. So in this case, right, for Friedel-Craft alkylation and acylation, there is no discount in terms of condition. All right, you just remain status quo. But normally 3 and 4 is not, the frequently asked question. Yes, we still need to study. We still need to prepare for it. Okay, so I'll just complete this very quickly. Heat, and we still need the catalyst, also known as our halogen carrier. Okay, therefore we will form this. Please make sure when you do your acyl chloride, when you draw it, make sure the ring is bonded to the C double bond O. Please do not go and join it to the CH3. All right, because a lot of us have a habit of writing CH3 first. Okay, that's careless mistake. So therefore, this is your 2 products form, either position 2 or position 4. Because OH is activator, therefore it will direct the incoming electrophile to position 2 or position 4. Okay, so in terms of the reactions of phenol, we are completed. All right, so if I were to zoom out to let you all have a look at the whole diagram, on the whole picture here. So these are the 4 reactions if you want to react with the ring part of the phenol. Okay, yeah. Now, yes, I would like to add one more here. Okay, yes, I will come to the last one over here. Okay, now I would like to add number 4. I use a different color. So you can see in general, phenol reaction, I will split it to 2 parts. Reacts with OH on the phenol, react with ring on the phenol. Okay, now the next part here is to do coupling reaction. Okay, coupling reaction. So coupling reaction is got to do with the OH part. All right, it's a last one here, number 4. So let me put number 4 here. Okay. So for those who have learned phenylamine chapter, all right, so you know that one of the reactions of phenylamine is to form azo dyes, okay, which is the diazonium ion. That's how we started, okay? So I will make the safe assumption that you already learned what is diazotization in coupling, and I bring the coupling reaction here, okay? Now, so let's look at coupling reaction. Okay, coupling. Now, so coupling is main focus is the benzene diazonium ion and triple bond N. Please remember the positive is on the nitrogen that is adjacent to the ring. Please don't go and put the positive charge on the top right corner. Nope. It's going to be on the nitrogen that has 4 covalent bond, which is the one directly next to the ring. Okay, so this is your benzene diazonium ion. Okay, and you want to do a coupling reaction with phenol. Now, must we couple benzene diazonium ion with phenol? No, you can couple with any other things. All right, you want to couple with, for example, a methyl benzene also can. You want to couple with a nitrobenzene also can. All right, so hence I put this as the last reaction. Okay, because it does not necessarily have to be phenol, but most of the time we will use phenol as the classic example to teach what is coupling. All right, so since it's also one of the possible reactions a phenol can do, therefore I will add up over here. Now, coupling reaction is the coupling between the phenol and the benzene diazonium ion. Okay, now when you couple up, what are the conditions? You need to make sure that the temperature is below 10. And because NaOH is being used, you need, phenol is being used as the coupling partner, you need NaOH. Okay, NaOH. It's for the phenol sake. NaOH is for the phenol sake. Okay, now then, when you couple up, the triple bond will open up one single bond, which is this one at the far right corner. So triple bond, you open up here. And this particular bond is a coordinate bond. It will directly attack the benzene ring of the phenol. So this is your azo dye, okay, which is used for coloring. It's a coloring agent, okay, yeah. So therefore, what we can see here is the benzene diazonium ion, they actually serve as an electrophile. Electrophile. Why? Do you see a positive on your benzene diazonium? Okay. Now, OH. OH is an activator. The incoming electrophile, in this case, is your benzene diazonium ion. They will be directed to position 2 of the phenol or position 4 of the phenol. So in this case, it has to be 4, not 2. It's because the benzene diazonium ion is a very big molecule. So unlikely it will be directed next to the OH group because of steric hindrance. So most of the time, we will direct the benzene diazonium ion direct opposite from the OH. So it's position 4. Position 2 and 6, unlikely. Okay, normally it's position 4 because benzene diazonium ion is big. So we can easily ask you to draw the mechanism, which is electrophilic substitution of the phenol with the benzene diazonium ion. So you just do it like how you practice your halogenation. and your nitration electrophilic substitution mechanism. So same thing, if you want to watch the electrophilic substitution mechanism, I'll also leave the link at the top corner on the video here. Okay, so all in all, if we were to look, okay, at the whole pathway of phenol, okay, so this is the whole picture. Okay, I started off with how do we form phenol, all right, which is the decomposition of the benzene diazonium ion. And then after you start to form a phenol, what can your phenol do for you? All right, so you can choose to react with the top part, all right, of the OH, or you can choose to react with the ring on the OH. Okay, yeah, so therefore this will conclude the phenol.